Okay, that's a good thing. Okay, so for example, I'm just giving example that in this problem, let's say, what we're going to do is that we know that the analytical solution of laminar flow in a pipe and the Reynolds number is 100. So I will discuss also this thing, what is Reynolds number, and the Y flow is laminar at this Reynolds number, and what will happen in the analytical part of the problem, and then what will happen in the CFD part of the problem. So for example, here you can see the figure that we have the pipe, and then we have the equation here. So this equation actually is not, I'm just writing the equation, but actually I drive the equation in this course. Okay, and then applying the boundary conditions, which are like on the center and on the wall. We have developed the equation, and this is like we have the analytical solution. And this comes from the solution of this differential equation. And then after that, we develop this problem in the CFD softwares, like geometry making will be done in the design modeler and the Spaceclaim. I will teach both softwares because they both have the advantages. So both should be taught to the students. And similarly, I taught the meshing. Meshing is like dividing domain into the small discrete parts. And on those discrete parts, we have the XYZ coordinates, and on those coordinates, we will solve our equations. So in the CFD, what is happening is that we are converting the differential equation into the algebraic equations, and then the software will solve them with the help of the matrix methods. Like you learn about the in your undergrad maths that there are some methods that can solve the matrix. For example, Gauss elimination, Gauss Seidel. But definitely the CFD softwares, the method will not be very much simple. They will be very advanced level. But I'm just giving you an idea that what is going to happen with those equations. So let's move here. So this is the detailed one. And these are notes from my batch one, which I have written on the slides. So we have taken the pipe, and the most important part of this course is that like, for example, I will go through the paper. For example, in the workshop number 4, we have the wind turbine. And in the wind turbine part, in every problem, we will start with the one statement. And then then we start to develop our problem. So for example, wind turbine case, I just have the one wind turbine problem at the TSR is equal to something, and this is wind turbine type. And then I develop the geometry starting from the aerofoil coordinates, and then the putting them in the required radius, then considering the uh, whole geometry, then domains and mesh, and then solution, and then comparing results with the available data. So first, like here, we are going through the definition of the laminar pipe flow, and that you can find in any good book. For example, you can refer to the Munson's book, and you can also refer to the Frank M. White's book. Both have the detailed analysis of the pipe flow. And also we have the one more book that is the Sengel. So this is example of the laminar flow and turbulent flow. So for example, this is the laminar part, transition part, and turbulent flow, which is happening here. Okay, so we have also derived the Reynolds number definition, which is ratio of inertial forces to viscous forces. And then finally, we come up with this formula. That formula you know very well. And then we discuss about how the flow is laminar, and when the flow will change into turbulent, what will happen to the local properties of the flow. And then we also discuss about the external flow, how we will be characterizing the flow when flow is external. So then how we decide about the flow is laminar or turbulent based on Reynolds number. So these are some values which we have given here, and I will discuss them also in the detail. And then I have gone through the one very typical case, that is flow around the circular cylinder. So we have discussed the different flow regimes, and also we compared the laminar flow and turbulent flow and what will happen in the both cases. And then we definitely our main point was in this workshop was to discuss the pipe flow. So then we started with the pipe flow, and you know about the pipe flow that it contains the two regions. One is the entrance region, and second region when the flow is fully developed. To discuss them, and based on mathematical analysis and theoretical analysis, and we have the equations like continuity equation, And here we prove that the ux is not a function of the z, so it's a function of the actually r. And then we have the momentum equation, x and y and z component. And from here we have actually proved that the pressure is only function of the axial direction, and velocity is only function of the r direction. And then we have the equation, and from this equation we have the boundary condition also. And the first thing that we have drive in this course, in this workshop, is that the link between the pressure drop and the wall shear stress, that is the shear stress on the wall. And the second thing, that is the derivation of the velocity profile, that is a parabolic in nature, this one. And we have gone through the whole details about the derivation, which you can find in some books, but here you can see this is a step by step. And then I went for the driving the maximum velocity and the average velocity in the pipe. And then I converted the velocity profile in terms of the maximum velocity and the average velocity. And second method also I given that you can also drive the same thing with the second method also. And then we have gone for the discussion of the boundary layer and the different parts of the boundary layer and how to resolve this one in the CFD also. And also discuss little on the turbulent part of the flow. So turbulent flow, we have the U plus and Y plus. And then we discuss about the pressure drop in the pipe, and actually we drive the whole equation. Okay, all these terms are explained in the course. And then we have the formula for the skin friction coefficient and also the Darcy friction factor. And Darcy friction factor actually you can get from the Moody's diagram. And in our course, we are concerned with the laminar region, but I discussed also that in different regions how you can find out the Darcy friction factor. And please, for your information, the Darcy friction factor, the formula will remain same. The only thing is that the value will be different for laminar flow, turbulent flow, and transitional flow. So in this way, we have found the values for our particular problem, numbers. And then we went for the CFD part. Okay. And CFD part, actually, our main theme was that how to find out the geometry and the fluid properties and the flow properties. So all of these were derived in this case. So then finally we come up with this definition. So this definition is based on the given problem and based on the theoretical analysis. And then we made the geometry in the design modeler and also inside the Spaceclaim. Okay, and then we have the geometry here, and the meshing part is requires some discussion. So we discussed the different options available in the ANSYS meshing. And why we did this thing, because if you go through the meshing side, so this meshing technique or these techniques will be same for every problem. The only difference would be that every problem will require the different specification of the cell size, the method, and the inflation layers. But overall, the method will remain same. That these options will remain the same for the all cases, but their usage will be different. And we discuss about the mesh quality and what should be the minimum quality we can accept for the CFD. We have also gone through the different mesh matrices and their qualities and their ranges are okay for CFD or not. So we have gone through all of these things. Then this is a general process that what should be the procedure for defining the meshing in the any CFD software. So then we have gone through all of these details. We discussed them in the very detail actually. And then I discussed about some of cases which I have solved myself. And I discussed that what will happen with the different meshing methods and where they should be used. So you can see that this is then finally I come up with a meshing of our circular cylinder. And here you can see this is a Hexa meshing, and it was done using the sweep method. And here I have shown the meshing from the 3 different methods that we actually use for our CFD mesh generation. The multi-zone method, the sweep method, they both will produce a Hexa mesh, hexahedron mesh. And then the third method is tetrahedron, that is will produce the tetrahedrons. but definitely with the inflation layers, you can see here. And then we have discussed about the plotting the different variables, like for example, on the center line of the pipe. This is the pipe. And on the center line, we actually plotted the velocity. So what's the point of plotting velocity on the center line? Because we know that in the pipe center velocity will be maximum, okay? And we know the formula that the U maximum will be equal twice the U average. And also we know that we are specifying the velocity at the inlet of pipe. This is equal to the U average. So this value we are specifying is equal to 1 meter per second. So it means that at the center of pipe, the velocity should be equal to 2 meter per second. But that's only possible in the region where the flow is fully developed. Okay. So from here, you can see actually that from 0 to 10, the velocity is changing. But after that, the velocity is actually approaching the 2 meter per second. It means that the pipe has the two regions, entrance region that we also found from the theoretical formulas, empirical formulas, and also through the CFD. This is a confirmation of our CFD and the analytical formulas. And then we have the pressure drop from the CFD and as well as from the analytical formulas. And we discuss also that in the entrance region, actually we have the nonlinear velocity pressure profile. So that cannot be actually will match with the analytical equations. So to compare them, either we have to compare them in the region where the flow is fully developed, or we can extrapolate our pressure profile from the latter region, and we can extend like in a linear fashion. And then I found that this pressure drop, which is 12.8, will match with these theoretical equations. So then I have discussed about the velocity profile plotting, like analytical solution, which we derived there in the very beginning, which I can show you here. This one. So this one we have derived with all the details like the velocity, maximum velocity, the average velocity. So then we plotted them side by side, and so that we can compare our CFD. And what we found is that the tetrahedron meshing has some problems in matching with the data. So you can see the tetrahedron meshing is over here. While the both SWIP and the multi-zone, they are matching very well with the analytical solution. And then we have these are the pressure contours and these are the velocity contours. And you can see that maximum velocity is happening in the center. And then we have the velocity vectors, and the velocity vectors actually, if you see them, this portion, you can see that this is like confirming the parabolic velocity profile, like the profile shape you see in the books. So this is like a very simple problem, but this will give you the lot of details about the working in the CFD and how to convert the problem from the statement to the geometry, meshing, and the boundary conditions and fluid properties. And then finally, how to compare our results and validate our CFD simulation from the known data. Known data can be like an analytical solution. It can be some good CFD. It can be also some experimental data. So for example, here, okay, any questions? Okay, so second case that I will be going through in this course is about the drag protection on the NACA 0012. So again, we start with the definition of the problem that we have to solve the CFD of the NACA 0012 at Reynolds number is equal to 3 million. And we have to compare the lift and drag and moment coefficients at 0 angle of attack and 10 degrees angle of attack. And we will use the different turbulence models and including the transition model. Transition model is a model that can actually model the both turbulent and laminar flow. So then basic definition of the aerofoil, different properties of the aerofoil. And then finally, we start with our problem definition and we will calculate our known values and the unknown values from the Reynolds number formula. And also I have given the X and Y coordinates for angle of attack when you specify the velocity at the inlet of the domain. And this is data from Abbott's book. And here actually, from this graph, we have taken the data at angle of vertex 0 degrees and 10 degrees, CL and CD. And this will be used for actually comparing with our CFD analysis. And this is a procedure to get the aerofoil coordinates from there's one website. Although you can get through your like equations for NACA 00 for NACA 4-digit series aerofoil. But at the same time, the more easier way is that you can get the coordinates directly from the one website that can give you the different options that you can even you can generate your own aerofoil. Like you can define the maximum camber percentage. You can define the location of maximum camber. You can define the thickness, and you can define the number of coordinates. Like they can be varying from 20 to 200. So you can make your own shape also. And after that, like you have to put them, these coordinates, like you copy them from here, you can put them in the particular format. This format I took from the design model help. And then I made the Excel sheet for that. There are two formats based on the trailing edge shape, like a sharp trailing edge and a square trailing edge. So here we use the square trailing edge. So I have given the both formats in the notes of this course. So like you have to just paste the X and Y coordinates and Z will be 0. And this is the total format. And then you have to paste these all values from Excel to the text file. And text file will be imported into design modeler and you will get the aerofoil inside the geometry. And then based on this geometry, we have to make the domain. And so this will be domain of this aerofoil. So aerofoil is here. And then we have to construct domain around the geometry. And then we have done the meshing. You can see here. So I will create 3 meshes, mesh 1, mesh 2, mesh 3. So I will call them as the coarse, medium, and fine. And then you compare them so that we can find out which mesh is going to give us the results that will not be changing further with the mesh refinement. So what I found is that if the coarse mesh is this one and Y plus values I kept less than 1 for all cases. So the CD was this. Second case, medium mesh around 35,000 cells, and fine mesh around 65 to 67,000 cells, and Y plus is less than 1 in every case, like 0.45, 0.6, and 0.8. This is the maximum value of Y plus in the coarse mesh, medium mesh, and the fine mesh. So what I found is that from the coarse mesh to medium mesh, error was only 1.78%, and then from the medium to the fine, the error was only 0.73%. So based on this result, I can say that even the coarse mesh is giving us a decent values. Okay, but I chose the okay, so but I chose the medium mesh because medium mesh and the fine mesh, they are giving us a less than 1% error. So definitely if the mesh number 2 and mesh number 3, medium and the fine, they are giving us the error less than 1%. So I will be choosing the medium mesh because both of them are giving the same results. This is the computational setup. So this is the boundary conditions we are specifying on the domain and on the aerofoil surface, no slip wall condition. And these are the methods we are going to select in the Fluent Fluent software. So I will discuss them also. That what is the meaning of the Y plus 10, Y plus 1, what is the meaning of the different turbulence models, and what is actually the Y plus. Okay. And these options which are I'm selecting here, they will be discussed here. And finally, these are the conditions we have actually derived in the previous slides, which are here. Okay. So these all are actually again given on our main slide. And then I discuss about the results. So these are notes from the previous batch. And then we have the convergence plot for the residuals, drag coefficient, lift coefficient, and the Y plus values for the medium mesh. And then results for the drag and the lift coefficients for different angles, for different turbulence models, for transition models. So these all things will be discussed in this course. The third workshop is about the Darrieus turbine. So Darrieus turbine is the type of the vertical axis wind turbine. And in this workshop, actually, we have gone through the theory first, and then we discuss about the reference which I'm using here. The reference is given here. So I took all the values from there. The profile was NACA 0015. So again, same procedure like we did in the NACA 0012 case. So I will go to their website, and from there I will take the NACA 0015 coordinates, and I will paste them in the proper format, in the text format, text file format, and then I will import them through the curve command, 3D curve command in the design modeler, and I will develop this whole domain like this in this same fashion. I will put this exactly same thing like I have just copied all the things from the paper so that we can compare our results with the results from the paper. And in this work, I have actually compared my results with the two TSRs. TSR stands for the tip speed ratio. And these dimensions are given in the paper. This table is also taken from that paper. Then based on this data, what we have the CP data from experimental data, which is drawn here. And also we have the data from the SST model. This is from this reference, okay? And these are the important formulas will be used for the analysis of this wind turbine. So then based on this data, I have actually come up with a Reynolds number for this case. And also I have derived the value for the theoretical power available in the wind at those conditions. And then I calculate the time step required for running my transient case. This case will be solved as a unsteady case. So I need to have the time step calculation. So I cannot give you the idea here right now because this will take like 30 to 40 minutes to explain the time step calculation. And then I have gone through my boundary conditions, material properties, reference conditions, and this is a procedure to actually import the NACA 0015 aerofoil. And this is a scheme for domain creation. And these regions you can see here, these ones, the circular one, they are required for the refining mesh around the aerofoil. And also we need to refine the mesh in the back region. So these regions are created to refine the mesh. And finally, you can see the mesh, which is created with the help of this domain scheme and the meshing scheme. And you can see also, we have the very nice Hexa meshing in the close vicinity of the aerofoil, and away we have the tetra meshing. So the whole overall procedure for the solution. So we will discuss them in the detail in the course. And I want to show you the one animation of okay, and also you can see one thing, that from the reference, their own work, the reference work, that their error was 8.8%, but based on our CFD, the error is only 1.38% with respect to the experimental data. Okay, so the reference we are using here, that reference has the error of 8.8% at the TSR is equal to 2.5, but in our case, error is only 1.38% because we have implied the very high quality meshing and we resolved the important flow regions. So this is the animation of the water shedding in the wind turbine blade, and you can see here. And this was made in this course, in this whole workshop. And then I have also given 3D case, but in this course, we'll not be solving the 3D case, but I will show you that how you can make the geometry for 3D case and the meshing. Next problem is about the volume of fluid. It's a multi-phase problem. And I took this very simple problem that we have the one tank, and on the bottom, we have the one orifice, like a hole. So from here, once we open the hole, this orifice, this will start to actually empty the tank. Okay, so In this workshop, the aim is that, objective is that we have to find out the time that is required to empty the tank for the given conditions. So we start with like a description of the problem, and then I have took the one formula from the book, that the time to empty a tank theoretical formula. So here we have the h is the height of the tank, that is the height of level of the water in the tank, and the g is a gravitational acceleration, which is 9.81. This capital A is actually the area of the tank, cross-section area of the tank based on the diameter of the tank, d. The small a is the area of the orifice, and the CD is the discharge coefficient. This is we took from the book also, and its value is given as for orifice. This is given as the 0.81. So we use this value, and we found the time it will take to empty the tank is the 4.3828 seconds. But you can see one thing, you can observe one thing, that when we use this formula actually assumes a constant height. Height is actually, you can see the height is equal to the pressure gradient, okay? Because rho GH is equal to the pressure. So it means that this formula assumes that the pressure difference will be same, that is a maximum pressure based on this height. But actually when we, as we are going down and down, so this height is reducing, okay? This height is reducing, and so the pressure. So when the pressure is high, the flow rate will be highest, and when the pressure difference is going lower and lower, the flow rate will be going down. So it means that this implies that the time will be more, because as the height is reducing, the speed of the discharge will be slowing down. It means that it will take more time actually to empty the tank, and that thing we will confirm through the CFD. So this is a scheme for the CFD. So we have the model the tank in the design modeler, and also we implied the Hexa meshing, because Hexa meshing will give you the best results for the multi-phase simulations. And these are all settings we have specified the multi-phase modeling for this case. Although this case looks very simple, but it requires a lot of consideration in setting a problem in the Fluent. So all these things are discussed in this course. And then I discuss about the time step size, and then you can see the animation here. So this is not a 2D case, this is a 3D case, but I have only shown the animation on the one 2D plane that is on the center of the tank. You can see one thing, that initially the speed is very fast actually. And this color shows, this is the blue color is the air, and the red color is the water. So water is going down, and that space is being filled by the air, definitely. Because anything empty will be filled by the air automatically. You can see now speed is slow actually. And see what happens in the very final moments of the tank emptying process. You can see now this is like it's very slow down, and it's like dropping from the tank bottom, not flowing. Okay. Yes, please. Yes, please.
Yes, I hope you can hear me. No?
Yes, I can hear you.
Can you hear me?
Yes, I can hear you.
Okay, I have a question. Why do we have like a colorful
Yes, please.
why do we have a colorful gradient between the interface? Like we have water below and
Yes,
air above.
that interface is actually, there are two issues here. One is that this shows that
Yeah.
this is we have the both fluids are here, means that it is interface. We have the both air and the water. Okay. And second thing is that the mesh is not very fine. If we have the very fine mesh, then we can have the very sharp interface actually. Okay. But for the
Okay.
demonstration purpose, actually, I could not afford to be having the very, very fine mesh. If I get the very fine mesh, then this will take maybe days to simulate the case. Okay.
Sounds good.
So
Okay,
that's
great.
why I
Thank
kept
you.
the mesh count low so that I can explain the process. Okay.
Okay. May I ask another question? Maybe it's not related, but
Yes.
I have a
Yes, please,
student
please.
license, right? I have a student license. I don't know if it will be capable of solving the problems in this workshop or no. Um,
The student version has all the capabilities. The only issue is that in the student version, that it can only solve up to the 512,000 nodes, sales. So not nodes, but sales. Okay. This is a limitation of
okay.
the student version. That's the only problem.
Yeah.
Okay.
And
And
our
also it
problems
allows
in
you to
this
have
work.
the, I think, only the one core. I don't know. Only, sorry, only one license that it can allow you up to, I think, 4 cores. That's the only problem.
Okay. Mhm.
Now, for example,
Okay.
if I discuss about this problem contains only 19,000 cells. So for this problem, student version will work very well, no problem. Okay. But if I discuss about the like a wind turbine case, that the Darrieus turbine, in this case, our mesh size is approximately 1,89,000. So this will also work here. Okay. So this will work for the, I think, 4 problems, but for last problem, that is the heat exchanger. In this problem, you have to reduce the number of cells, then it can work. But right now, like I have the around, I have created 2 meshes actually. One is through ANSYS meshing, and one I was teaching to somebody, and I created in the Fluent meshing. So the meshing in the through ANSYS meshing, it contains the around 5.2 million cells. Okay. So definitely student version will not be able to solve it. But if you can reduce the number of cells, like you can reduce the number of cells to the very low value, like 512 thousand, 512,000, then it will handle the problem very well. No problem. Okay. So either you change it to the professional version that I am going to provide you in the WhatsApp group. Second way is that if you are not allowed, let's say you are living in the country that you are afraid of getting caught with the correct version, then in that case, I would suggest that you can reduce the number of cells to the in the range of the 512K.
Okay. Sounds good.
Okay.
Thank you. Yeah.
So either reduce the mesh count or use the professional version. Okay, so for the first 4 cases, you can actually use the student version very easily, no problem. But for the fifth problem, heat exchanger problem, you have to like have the either reduce the number of sets, or second thing is that you have to uh, like use the professional version. And I have the correct version. I will share with you. Any questions?
Hello,
Okay,
sir.
so then in the yes. Is anybody else? No questions? Okay. So last problem is the heat exchanger design using the CFD. And here we have to like, I will go through the some theory of the heat exchanger. And I will design also like different variables. I will discuss about theoretically, analytically. And we start with the design, some design parameters, we start from there. But even if you want to go further, then I would recommend that you can go through the heat exchanger book by the Shah. You can search on the internet, heat exchanger book by the Shah. So if you want to design from the very, like from scratch, like you want to design everything from you by yourself, then go through the Shah's book, and it has the nice empirical formulas. It can give you idea that the how should be the every each and everything in the heat exchanger should be designed, even including the heat transfer rates, the pressure drops, number of tubes, number of baffles, size of the each and every tube. All things are discussed in the Shah's book. Okay, so refer to Shah's book and you will get the complete knowledge. But here we started with some basic information was there. But the missing thing here is that I have the temperatures, but we don't know the flow properties. What should be the flow properties entering to the shell and also entering to the tube? So then I have gone through the basic methods, log mean temperature difference method. And from here, actually, I found the values for the flow rates for the hot side and the cold side. And from the mass flow rates, actually, I found the value of the velocities. So these velocity will be now input for the, this is shell, shell condition for the shell inlet. And from the cold fluid side calculation, we found the flow rate. And from flow rate, we found the velocity we are going to enter into the tube side. So geometry, before that, we discussed the different parts of the heat exchanger. And in this course, actually, I took the very modular approach. Modular approach in a sense that I started with a very simple design, like a single tube and the one shell pipe. And the dimension will remain same. These basic dimension will remain same. Only thing is that we are going to add the different parts here, and then we will try to make it like a real one, real case we can see in the industry. So yes, definitely they are applicable. Yes, time step calculation is exactly, definitely the numbers will be different, but time step calculation exactly same. But it can be like for different cases, it can be different in not in a process, in a concept, but it can be different. For example, for aerofoil, if you want to analyze the transient flow at high angle of attack, so are the flow around the circular cylinder like a water shedding. In this case, if there's some water shedding around the circular cylinder like this one, then I would be going for the dominant frequency. So we have the methods to discuss. How you get dominant frequency? Actually, I will get dominant frequency from the stall number. Okay, and stall number we can get the actually frequency. So and based on that frequency, we can get the total time it will take to pass the one vortex shedding cycle. Okay, so this is time to for the one vortex shedding cycle. This will be time we can find out by the formula 1 upon f, because the frequency is actually a 1 upon second. So if you divide 1 by the frequency, you will get the total time it will take to pass the one cycle of the that flow. So then from based on this flow, actually you can divide into multiple parts. So the procedure is same, but for different cases, there will be different scenarios. Okay. So best way would be that, for example, if you learn about the how to calculate time step, then you will go, for example, you will go to that particular problem and find some papers or thesis. And from those papers, see that based on which factor they are determining the time will be spent for that particular flow. And then that once you get the time, then dividing time into time step is very easy. Like you can divide them into 40 steps, you can divide them into 100 steps, you can divide them into the 200 steps. So maybe the question will be there. Then what should be the like a value? So for example, if you get the time, so delta T you can find out by dividing total time into number of steps. Okay, number of the time steps. So you can start like maybe you can divide the time by the 100 time steps, and you get time step for the each and every time step. Okay, so this is time for the each and every time step. Second case would be that like you can get a second time step by dividing total time by the maybe by the 200. Third time step you can get by dividing time by the 50 time steps. Okay. and then compare the results for time step 1, that is the T upon 100. Second time step, that is T upon 200. Third time, that is T upon 250. And in all time step, you can see the difference is like a twice. Okay. And then you can compare your results that okay, now if the results are changing with the time step change, then you can continue like dividing in this way. Like for example, the four time step may be T upon 400. So, and then where we'll stop where when the time step, if you reduce time step size, it will not affect the solution. So once the effect of time step reduction is you cannot see in the solution, then you stop there, and that's a required time step. That's how you actually get a time step. For combustion, for example, for combustion, the time step different may be the based on the different parameters. For the pipe flow, transient pipe flow, the time step criteria maybe is different. For the wind turbine time step calculation is based on the different terms, but the basic concept is same. Okay, the basic concept is same. The meshing process is the same for all cases. Like we have to have the define the method, then we have to define the size. We have to specify the inflation layers. We have to specify the for turbulent flow, the Y plus value, which required Y plus value should be we can get. If you don't get it, then you can also come back in the meshing software and define the mesh. And you refine the mesh until you get the required Y plus values. So the all procedures are exactly the same. Yes, like dominant frequency is about the circular cylinder. So when discuss about the like a von Karman vortex, the von Karman vortex state, in that case we discuss about the dominant frequency. But in this course, we are not actually going for the that problem. But we are going here. We are going with the wind turbine. We are going with the tank emptying. So in the tank emptying, how I did calculate time step, you can see here. If you take a look here on the wind turbine, okay. So in the case of wind turbine, how I get the time step idea is very simple actually. Okay, if you take a look here, what we did is that we found the time that it will take to complete the one revolution. So revolution means that starting point is this one. So we go along the circumference and you come back again to the same point. This is the one circumference. Okay. And the speed of the our flow of the wind turbine is equal to the uh, omega into r. Omega is the radians per second, and r is the radius of that particular location. So from here, we actually found the transition velocity. And so we know that the formula for the time, the velocity or speed is equal to, the speed is equal to distance upon time. So the time would be equal to distance upon speed. So if you put the value of distance and the value of speed, you can find the time it will take for the one complete revolution. So now in the case of the wind turbine, what we have learned in the from the papers, that they say that you have to like study the effect of time step on the results. Which results? Definitely for the wind turbine, the torque is the important parameter. Okay. So what they say is that they say that okay, you have to like divide this whole time. This will take to complete one revolution by the first will be that you have to divide by the 360 degrees. Means that actually you are solving for each and every time step, you are solving the 1 degree. So for every time step, the wind turbine will forward by the 1 degree. Okay. So first time step, it will forward by 1 degree. Second time step, it will forward by the second, like 2 degrees. Third will be 3 degrees. So what we are doing here? Actually, what we are doing here is that, for example, this is a wind turbine blade here. Okay. So after one time, say blade will be here. So we observe the value of this. We will get solution of wind turbine at this time, at this angular location. So what we get here is that we get the torque value here. We get torque value at second angle. We get torque value at third angle, fourth angle. So we get the torque values on the all time step. And all time steps, actually, they are time steps are corresponding to the its angular position. So what we are doing is that we are simulating the, we are reproducing the what is happening physically to the wind turbine. So at each and every time, that's also we do in the reality, that when you are doing the lab test of the wind turbine, actually you have the sensors that can record the value of torque for the each and every position of the wind turbine. So from there we get the a torque value for one evaluation. Then you can get the torque maybe for 5 cycles for the 5 evaluations for the, and then you can average them. So after averaging them for the 5 cycles, you will get the every value of torque for the whole wind turbine. That is, it's going to produce when it is going to rotate in the one cycle. Okay, then why we are making it 5 cycles? Because the one cycle can have the some maybe data biasness, but if you take the 5 cycles, you can average out the any peaks in the solution. So that's why we recommend that you at least take the data of 5 cycles and then average out data and get the average torque on the wind turbine blade. Okay. So the CFD of the winglet will be same. Like a winglet will be affecting the left hand drag, and also it will be affecting the wingtip vortices. Okay. So procedure same, geometry making same. You will define the boundary condition in exactly same way. You define the domain in exactly same way. But definitely you have to now also you're the winglet on the wingtip, and here you will be defining defined mesh on that part. Okay. So, but I will be giving you one this is a very good joke actually. So there was a person, and he gave the tutorial on the YouTube how to make a red chair. How to make a red chair. So that was available on the YouTube, that how to make a red chair from the very beginning. So somebody commented on the in the comments that can you give me tutorial how to make a green chair. Okay. So now point is that if you if you can make the red chair, so you can also make the green chair. So only difference is the color. So the basic idea is same. So you can the human brain can process the knowledge, and it can actually apply this knowledge on the similar problem very easily. And with a simple tweaking, you can also apply knowledge on the some different problem as well. Because the CFD process is like a modular process, and the software does not know that you are solving the wind turbine, or the wing, or the winglet, or the aircraft. It does not know. It only knows that we have the some coordinates x, y, z. We have some equations, and then we have the matrix, and the computer is actually solving those equations in the matrix form. It will get the values for the different variables, u velocity, the x velocity, that is u, y velocity, that is the v, and z velocity, that is the w. And also it will be solving the pressure field. It will be solving the temperature field. If there's a temperature also involved there, it will be solving the density and viscosity if they are function of temperature and pressure. So like that. So the software does not know you are solving what thing. So you have to understand that how you can input the data. So you have to divide first you have to make the geometry. Then you have to make domain. For internal flows, you have to get the extra internal volume. For external flow, you have to make the domain, a control volume around your geometry. And then you have to divide into the discrete parts, that is a meshing. And then you take it to the CFD solver, where you will define the boundary condition, material properties, reference condition, the correct physics modeling, like a turbulence. If this is a combustion model, then which combustion model will be the best suitable for your case, like that. And then you solve the case, and then you analyze the results and you post process them. Like you divide, you put them in the different formats, like the contour plots, vector plots, path lines. Maybe there are some particles you want to track them. Then the track, there will be the particle tracks you can release on the CFD post part. So this is the way we actually analyze the problem in the CFD. So understanding the problem is a very important thing, and then how to convert that problem into the numbers, and that note those numbers how to be getting the geometry, making the proper setting in the CFD solver, meshing, and then analyzing results, and then like comparing with the known data. And even if you don't have the known data, like any analytical solution is not possible for that problem. If you don't have any numerical solution from some other person, you don't have any experimental work, and even in that case, you should be able to actually compare your results. That you can have the some sense about the results, what should happen with your case. Okay. And also keep in mind that the CFD is not about the data matching with the external data, but it's like a process. So when you create three meshes, like a one mesh, second mesh, third mesh, coarse, medium, fine, like that. So actually, this is like we are comparing our own CFD with our own CFD. Okay. So why this is so? Because the scientists found that the meshing, boundary conditions, your correct physics has a lot of effect on the your CVD results. So you must first check these things. And once you are done with these things, then you can go for the other aspect of the problem validation. Okay. So yes, the answer is that you will be able to solve any problem if you learn the problems, if you learn about the few problems. But definitely, for some other problems, there will be some little change will be there, some little addition will be there. So you have to understand that thing, maybe theoretically. If not, then you can also go to some papers, and from there you can find out that how they actually tackle that problem. So basic things will be remain same, but maybe there will be some additions. So okay, so in the same way, like we did here, we are going to solve the heat exchanger problem. So again, the geometry making, we have created the meshing, and then we solve the case. So then we will go on, and we will actually will be creating the 5 designs in the Spaceclaim. So the last design, and based on some calculations, definitely. So the fifth design is the which contains the baffles and the tubes. So from single tube, we are going for the 5 tubes, and based on the same flow rate. And from the without any baffles, we are going to introduce baffles, and baffle will actually will maximize the time and the contact region between the shell fluid and the tube fluid, so that we can have the maximum heat transfer. And the meshing is also discussed in details here. So like this is the what you have learned in the first workshop, like the different methods, different techniques, how to define the sizing, how to define the inflation layer. So you will all apply these all things in this workshop. This will be like application of all the meshing methods. And then how to define the problem in the Fluent software, the fluid properties like a hot fluid and the cold fluid, solid material properties like tube thickness. We define that as a copper, and then we define the properties for the shell fluid and the tube fluid. So we discuss about the Y plus values also, and solution convergence. So based on the residuals, and also you have to plot some important variable in the some local location. So based on that, once they make a straight line, then we can say the solution now actually converged. So only based on the residual plots, we cannot alone say that the solution converged. Sometimes they can be misleading, like they can be straight lines, and we can say solutions converge, but no. we will plot some variables of interest that is important for our simulation. And once they converge, they are not changing. And then only can we say that solution is actually converged there. So here we can see the all 5 designs, the temperature contours and the path lines. And this is the the numbers, the shell outlet temperature theoretically, and from the designs, design 1, 2, 3, and 4 and 5. You can see that as we are going to design number 5, it is approaching to the theoretical value like this. Not exactly same value, but it is actually approaching to theoretical value. Okay, so this is the end of this demo class. And actually slides are when we are going through the for example, if I take 1 minute, just give me 1 minute. Actually putting everything in the slides is not possible. And this in that case, the slides numbers maybe will go to 500. So that's why we are giving the video course. So the slides only contains the important information. Okay. Now I cannot give the when I said the pressure based solver, I give the one picture and the slide. Then when I said the transient problem, then I give the picture that we are setting this time step and number of time steps. Then we define the gravity in that direction, and I will give that picture. So this will making the, and definitely you cannot give the like a geometry cleaning in the slides. Okay, not possible. So for example, here this is a heat exchanger model. Okay, and which you discuss actually in the course. This is a very random design. I just took it from the some GraphCAD website without knowing that which design it is. So we will go with this design. Okay, so how to get the control volume, how to get the fluid volume from these random geometries. So this is how we are going right now. Okay, so for example here, okay, I'm extracting files here and opening the Spaceclaim. Uh, there's one thing that we can see, that when you go along the course, actually you will learn these all things. Okay. So, but because you asked me, I will going to give you some idea here. Okay, one more thing I want to show you is that, for example, here, what we did is that we have gone through we have the two reference for NACA 0012. The one is we have from the Abbott's book, and second is from NASA website. So what I did is that I have this reference here, for example. So this is the data because we are solving the Reynolds number 3 million case, and we are solving the both cases, the free transition also, and also the fixed transition. So fixed transition is when you're solving the fully turbulent flow. Okay, and our Reynolds number 3 million. So this is from the Letson, the green color. So in this course, I have shown that you can also get data, like you can reverse data. So you can reverse engineer the graph, and you can get from graph, you can get the numbers in X5 fashion, like in the Excel. So that also I taught that we can convert the graph into numbers. And secondly, if you go through this data here, you can see that we are comparing with the Letson data. Okay. So I went to the lesson data, and what I did is that I went to the Reynolds number is equal to 3 million, this one, fixed transition, and the angle is equal to 10 degrees. For example, here. This data was copied up to here, up to this point. Okay. So we took the data, like this is data, we took it from the graph and converted it into the XY values. And this data is directly copied from this website. Okay. So what we did is that, for example, here, if I go back here, to copy data and paste in the Excel. Second thing was that, for example, here, this is the CP plot for the 10 degrees angle of attack. So I copy it and paste in the, like over here. Okay. And save the file. Okay. So here we have the, like, so we have the one software that is a web plot digitizer. You can use it online. You can also download that software. There are many softwares for that purpose, but I use this software actually. So launch it and go to images, file, and load images. Okay, sorry, not this plot, but this plot. Yes, this plot. Okay, so do it again. This one. First thing is that we have to align the axis. So like this is 0 and 1 here. Okay. In a similar way, we have to align the y-axis. So y1 and the y2. So put the x value, which is 0 to 1, and the y value is from 0 to, so sorry, 2 to minus 6. Okay, so we are comparing the lesson Reynolds number 3 million data with the fixed transition. So like you have to click on these green triangles and try to put them as accurate as possible. Try to put it in the center of the triangles. So then you go to the view data, and from here you can get data in the XY format. Okay. And same data actually I pasted here. Here. So this is like from that graph. This is directly from the website. Okay. And this data is from the CFD. And the case is the 0 angle of attack. Sorry, this is 10 degrees angle of attack. So here you can see that the data is matching very well with the lesson data from NASA. So definitely NASA people, they are doing the great work. We did the very like a first try, and what we get here is that you will have to go through the these references and see that the how much what are the mesh size they are actually using in this case. Okay, so I don't remember the mesh size they are using for the NASA case and NACA 0012, but actually we are getting the very close data. Okay, we are getting very close data with the NASA's data. Okay, so anyhow, so our discussion was like how to like a cleaner model. Okay, so this is the like heat exchanger case. Okay. Copy, and so I'm copying the path actually. So now I will click on the open file, and I will go to that particular directory or folder. So look for all files. So here I'm going to import the like some geometry CAD model. So tube shell and the tube assembly 1. I think this may be the main part. No. So let's try second file. Okay, I'm trying to find out the file that is like contains a full model. Hmm. Okay, so here, if we take a look on these parts, so let's say if we go to the prepare menu and the volume extract, so take these two surfaces. So I will explain this thing, but I'm just giving you the commands that I'm going to use here. And click on the green tick mark. Okay, so it means that the geometry is actually not close. So let's take second example. But if the geometry has a problem, then we have to repair geometry first, and then we can use the different commands in the Spaceclaim. Okay. So let's say I want to take the volume, get the volume here. Okay. So I will take these two surfaces. So you can see that we have just got the fluid volume, this one. So this is the procedure that we can use in the Spaceclaim. So we just need this fluid volume, and definitely we have to like create an external volume that will be simulating the air, and inside this maybe there's some liquids there. Okay. Okay. So anything else? Okay. Anything else? Any questions? Yes, please.
Yeah. Another question. I believe I will not be able to attend in real time the
Hmm.
presentation, so I was just asking if you are going to post the recordings on our group, on
Yes,
our
definitely. You can
WhatsApp group.
see here.
Yeah.
Uh, uh, for example, here you can see this is like from batch one student. He says, I got them up. I got them up till now. There are 11 classes.
Yeah. So you will
So
send them on the
this is like
WhatsApp or
in
to the email.
the CFD course batch one. So here I actually regularly, this is today's my chat. So actually I send the videos on the regular basis. So here is
Oh,
it's
okay.
like a complete folder. So after like 1 week, I send the complete folder, which contains up till whatever we have the slides, we have the files, whatever we solved there. So these all things are like compressed in the zip format, and I upload them on the Google Drive. Although when you attend the class, when you register for the course, I have your emails. So when I will be creating the Zoom links, actually I put those emails in the Zoom invitation. So whenever you get Zoom invitation, even if you don't attend the class, whenever there's a
Mm,
meeting, that meeting will automatically will be sent to your email ID by the Zoom, not by me. So you can go through that link and you can download the files. But anyhow, because sometimes the students they don't get, maybe don't get the time, or they don't understand the whole procedure. So to make the thing simple, I download those files from the Zoom website and I arrange them in this way. Like class 1, April 17, class 2, April 18, class 3, April 19, class 4, April 22, so like this. Okay. So I place them, even the names also I put there, and then I just compress them and send to via the Google Drive.
yeah.
Okay.
But yeah, but this you do it on a weekly basis. If I want to have it like,
No, no, no,
you
no.
know,
This is
because
not a
of
weekly basis. This is on the daily basis.
daily basis.
Yes,
Okay.
this is a daily basis. I compress the whole folder on the weekly basis, whatever is done, so that I can have the that is for the only like extra security. Okay. Otherwise,
Mhm.
on the like for example, this is a recording for class held on April 30. So April 30 was when it was.
Okay, and that,
It was like April 30 was on the Thursday. Okay, Thursday.
yeah.
So this was like I just sent it on the same day. Okay.
Okay, that's
And
great. Yeah,
similarly,
yeah.
I send the
Okay,
meeting
so
links. Although you get the link from the directly from the invitation link directly from the Zoom, but anyhow, I put the these invitation links also before the class in the WhatsApp group.
okay, okay. So basically, we'll get the links on the WhatsApp group and on in the email as well, in the inbox,
The
right?
main communication is like through the WhatsApp group. But
Okay,
I
so
do send the things also on the email IDs because I have the all the data I have with me. Uh,
okay.
no, no, both. Sometimes people don't want to attend the live classes, so they will be getting recording only. They can join the class anytime, but they because this is a I have seen this thing in the batch one that the people I have the 12 students, and some of them they are not attending. They are only relying on that. There's a time difference there, so they are relying on the recordings only. Like I am teaching class from 7 to 9:30. At that time, there is a very early morning in the in the USA, Canada. So maybe they are going for the classes. They are going for the offices. So they cannot attend the a live classes. So they rely on the recordings. That's why I give the recordings them also. Okay. Thank you, Sheikh Sadiq. Thank you. Okay. So now I will be ending the meeting right now. And if you have any questions, you can send me on the WhatsApp or through the email or through the whatever medium you have found me. So I will answer you. I will try my best to answer you. Okay. Thank you. Thank you. Bye
Okay.
bye.
Have a good evening. Bye.